All right, if you guys are watching this, it means you stuck clear through the end and you guys checked out every slide of this PowerPoint, so good job for that. But this is your guys' answer key for the review, which obviously knowing the right answers and that you guys are on the right track will help you greatly for the test. So I'm just going to kind of go through this, some of it quickly, some I'm going to give a little bit more of an explanation to. But as you guys know, there was two parts to this. Part one focused on temperature versus thermal energy, and part two focused on energy transfer. So let's go ahead and just dive right into part one. Okay, so what is kinetic energy? It's the energy an object has because it's moving. Remember when we look at temperature and molecules, the higher the temperature they are, the higher their average kinetic energy, meaning that those molecules in that object or that sample are moving a lot faster. Okay? All right, what is the difference between thermal energy and kinetic energy? Both of them have to do with the kinetic energy of molecules in an object, but your temperature is the average kinetic energy. So you remember you add up all the kinetic energies and then divide through by however many molecules you have. Okay, thermal energy, on the other hand, is just your total. So you just add up those kinetic energies. You don't divide. Okay, so your total should be more than your average when we're talking about temperature versus thermal energy. All right, on the next slide, you guys needed to calculate the averages. So your first answer is 10.4. That number represents all 7 of these numbers here. So if you guys didn't get that right, make sure you guys add them up correctly. And then don't forget to divide by 7 because we had 7 numbers. Okay, next one, 5.3. We had 10 numbers on that one. Third one, 20. We had 3 numbers, so add them up, divide by 3. And then on this last one, we had 5 numbers, so add them up, divide by 5. You guys should get 16.5. All right, moving on. The next 3 slides all kind of ask you guys this question and then have you guys highlight the option that works best or describes the statement best. So for this slide, we're looking at molecules that are going to be moving faster. So our options were 20 milliliters of water at 87 degrees Celsius, 20 milliliters of water at 78 degrees Celsius. So if we're just looking at one molecule, this first one here that's highlighted at 87 degrees Celsius has a higher temperature. Therefore, all the molecules have a higher kinetic energy and are moving faster. Okay, next one, 10 milliliters of water at 10 degrees or 20 milliliters of water at 10 degrees. Both of those are the same. They both have the same temperature. Therefore, all those molecules have the same average kinetic energy and are all moving the same speed. Okay, number 3, 20 molecules of water with an average kinetic energy of 18 kilojoules or 20 molecules of water with an average kinetic energy of 22 kilojoules. This one I straight give you the average kinetic energy. So the higher average kinetic energy, the faster they're moving. So 22 kilojoules, your second option there is correct. Okay, 20 milliliters of water at 10 degrees Celsius or 40 milliliters of water at 100 degrees Celsius. So it doesn't matter that this sample is bigger because, again, we're looking at one molecule. What's its average kinetic energy? That's the temperature of that sample. This one has a higher temperature, so therefore all those molecules in that 40 milliliter sample are moving faster. Okay, 2 molecules of water with an average kinetic energy of 10 kilojoules or 10 molecules of water with an average kinetic energy of 10 kilojoules. Again, same kinetic energy there, so both are the same. They're both moving at the same speed. It doesn't matter how many molecules you have. Okay, we're looking at the speed of the molecules. All right, 100 milliliters of water at room temperature or 5 milliliters of water at room temperature. Again, both are at room temperature, so both have the same average kinetic energy, so all those molecules are moving the same speed, so both are the same. All right, for this next one, we are looking at lower average kinetic energy. We can also relate that to a slower speed, okay? So lower average kinetic energy, again, we're looking at a slower speed there. So for this first one, we're looking at 78 degrees Celsius because that is lower in temperature, therefore lower in average kinetic energy and lower speed. Okay, 10 milliliters of water at 10 or 20 at 10, both are the same. 20 molecules of water with an average kinetic energy of 18. So that one just straight up tells us this is the lower kinetic energy for the average. Okay, 20 milliliters of water at 10 is your answer here. Again, it has a lower temperature, therefore lower kinetic energy on average, and those molecules are moving slower. Okay, 2 molecules of water with an average kinetic energy of 10 or 10 with an average kinetic energy of 10. Both are the same because they have the same average kinetic energy, so they're both moving the same speed. And then finally, both are the same for this last one as well, because again, they are both at room temperature, therefore they are both moving the same speed. All right, last little one for part one. We're looking at higher thermal energy. So this one's a little bit trickier because remember that thermal energy is the total kinetic energy for those. Okay, so size of the object is going to matter here, size of the sample. Okay, so 20 milliliters of water at 87 or 20 milliliters of water at 78. These two are both the same size, so we're going to rely back on temperature here. If we were to add up all the kinetic energies of all these molecules and find the total or the thermal energy, 87 degrees would be our higher thermal energy there. Okay, 10 milliliters at 10 or 20 milliliters at 10, both are the same temperature, but because there's twice as many molecules here, we're going to have a larger thermal energy here. Okay, remember again, I can't say this enough, thermal energy is your total kinetic energy. So if you were to add up all the kinetic energies of all those molecules, the one that has the larger sample probably most of the time is going to be better, but temperature does matter there as well. Third one, a sample of water with a total kinetic energy of 18. So notice the difference in the verbiage here. I used total versus the last two I used average. So this one's just a straight up which one has the higher total kinetic energy. And in this case, 18 kilojoules is higher than 14. Okay, 20 molecules of water with an average kinetic energy of 18 or 20 with an average kinetic energy of 22. If we were to look, they have the same number of molecules, but these molecules in our second sample have higher kinetic energy, so we'd also have a higher thermal energy there. Okay, 20 milliliters of water at 10 or 40 milliliters of water at 100. This one not only is a bigger sample, so more molecules to add up, but they also have a higher average kinetic energy. So this one would definitely be way higher than this one. Okay, second to last, 2 molecules of water with an average kinetic energy of 10 or 10 molecules of water with an average kinetic energy of 10. This is about 5 times larger, so I would guess that our thermal energy would be probably about 5 times larger for this second one, since they both have average kinetic energies of 10. And then finally, 100 milliliters of water at room temperature or 5 milliliters of water at room temperature. Although they're the same average kinetic energy because they're the same temperature, we have twice as many, or excuse me, 50 times as many molecules there. So definitely that first one. Okay. All right, moving on to energy transfer. Okay, so on these ones, what you're going to see is we're going to look at 2 samples. If it helps you guys out, I hope you guys got a piece of scratch paper. If you have like a marker board or something you guys can work with, objects that you can use, it really helps represent these. I think I'd have a hard time doing these if I couldn't draw out a little image of these. So you guys should know what those images look like based on what you've seen in some of our past activities, including 3.1 and 3.2. All right, so sample A contains 4 molecules, each with an average kinetic energy of 15 kilojoules. Sample B is the same as sample A, 4 molecules as well, but has an average kinetic energy of 11 kilojoules. So let's just take a look at what one of these might look like. I'm going to go ahead and just duplicate my slide here. I'm going to erase everything that's on it, and I'm just going to use my draw tool to draw this out. Okay, so I have sample A and sample B. So this is going to be my A, this is going to be my B, and then each of them have 4 molecules. Those are some solid molecules. And you guys could do like little X's, you guys could do little dots, but what we see in this is our first sample A has an average kinetic energy of 15 kilojoules and B has an average of 11 kilojoules. So that means if we were to look at one molecule in A, it would have 15 kilojoules. This molecule would have 15, this would be 15, and this would be 15. If we were to add all of those up and divide by 4 to find the average, your average would be 15. Same with B, except they are going to have 11. So each molecule has 11. If we were to add those up and divide by 4 molecules, then you would have an average of 11. All right, so let's take a look at this then. Which sample would have a higher temperature, sample A or sample B? Sample A has the higher average kinetic energy, so that is your answer there. In which sample are the molecules moving fastest? Well, higher kinetic energy also means a larger speed, so sample A as well. If we looked at only one molecule of sample A, what would be its kinetic energy? 15. If we looked at one molecule of sample B, what would be its kinetic energy? 11. So there's 15 and 11 right there. And then what is the thermal energy of sample A? So again, remember thermal energy is the total. So you guys would need to add those up. Each one has 4 molecules, so you guys could either add up 15 4 times and 11 4 times, or you could take 15 times 4. So your answer for this should be, oops, sorry, wrong side, 60 kilojoules and 44 kilojoules. So 15 times 4, 11 times 4. Okay. All right, moving on, same thing with this next one. I'm going to go ahead and duplicate this slide so you guys have my sweet drawings for the next one as well. Oh, sorry, I'm not quite done with that yet. All right, so if sample A and B came into contact with each other and were allowed to reach equilibrium, which way would the energy transfer? So remember that energy always transfers from the warmer object, the one with the higher kinetic energy, to the cooler object. So in this case, we're going from A to B. A had 15 kilojoules on average. B had 11. So you higher number, so A to B. Okay, what would be the average kinetic energy? So if you guys look at this, I kind of did it this way. I said, all right, the energy is going to transfer this one from our hotter to our cooler. So that means these molecules here are going to give up kinetic energy to these. So this is kind of how I did this. I kind of did a little, you get one and you get one. So I took one away from each of these 4 molecules. So now they only have 14. And I gave them to these. And now they have 12. Okay, we're still not at equilibrium because remember, equilibrium is where we have the same average kinetic energy for all of those molecules there. So we're going to need to do it again. So I'm going to go grab a different color. Now I'm going to take one more away. We have 13, 13, 13, and I'm going to add those over here. So again, we'd have 13, 13, 13. Okay, kind of messy for you guys. The other ones are a little bit easier, not quite as many, not quite as high of a number for you guys. All right, so at the end of this, when we've hit equilibrium, every molecule every molecule in sample A and every molecule in sample B have 13 kilojoules of energy. They are at equilibrium. Okay, so 13 kilojoules, that would be your average kinetic energy for A and B. And then what would be the final thermal energy? Notice that that's not the same. So you guys would take, all right, we have 13 here, add those up, or excuse me, it is the same. Notice we have 13 here, add that up times 4. And then same here. But that's because your guys' sample is the exact same size. Okay? Versus the other ones you guys will come to, you guys will notice that because they're different sample sizes, they're not going to have the same thermal energy when they're at equilibrium. They'll have the same average kinetic energy or temperature, but not the same thermal energy. Okay? All right, moving on. I'm just going to go through the answers on the next one. You guys can kind of figure that out on your own. All right, so next one we're looking at sample C and D. Oh, of course, my computer just froze up. There we go. Okay, so sample C and D. Sample C contains 2 molecules each with an average kinetic energy of 1 kilojoule. Sample D contains 8 molecules each with an average kinetic energy of 6. So sample D is much bigger. Which sample would have a lower temperature? That's sample C. And they're also having the slowest moving molecules because they have the lowest average kinetic energy with only 1 kilojoule. If we looked at only one molecule of sample C, what would be its kinetic energy? 1 kilojoule. 6 kilojoules for sample D. And then what is the thermal energy? So again, if we added all those up, all 2 molecules at 1 kilojoule each for sample C, you'd get 2 kilojoules, and 48 for sample D. Okay, if we were to push sample C and D together and let them reach equilibrium, we have these questions. Which way would the energy transfer from sample what to what? Well, sample D was our warmer sample, so it would transfer from sample D to sample C. Okay, and what would be the average kinetic energy of sample C at equilibrium? They would transfer until all those molecules in sample C and D each have 5 kilojoules of energy. Okay, so that should be the same at equilibrium versus if you guys see this example compared to the last one, because sample D was so much bigger, your thermal energy will not be the same at equilibrium because again, thermal energy is that total versus your average is divided by however many molecules you have. So you'll have the same average kinetic energy, but not the same thermal because D is larger than C. All right, last one, we had sample X with 3 molecules, each with an average kinetic energy of 2. Sample Z contains 6 molecules, so it's a larger sample, but notice that they have the same temperature or the same average kinetic energy. So this one was kind of a trick one because I didn't give you guys the option. You guys saw in the instructions that you were supposed to kind of say whether they were the same as well. So at any rate, which sample would have a higher temperature? In this case, they both have an average kinetic energy of 2 kilojoules, so they have the same temperature. Trick question. In which sample are the molecules moving fastest? Again, they are the same because they have the same average kinetic energy. If we looked at only one molecule of sample X and sample Z, what would be their kinetic energies? Again, both would be 2 in this because they have the same. So it's kind of like they're already at equilibrium. And then what is the thermal energy of sample X? Notice it's smaller, therefore our thermal energy is smaller with only 6 kilojoules and 12 kilojoules here. All right, moving on. Which way did or would the energy transfer? You would have no energy transfer at all because it's already kind of at equilibrium with the 2 kilojoules of energy per molecule. Again, X and Y would have the same average kinetic energy. And then what would be the final thermal energy of sample X? Notice that Z is larger, so twice as large actually, so your thermal energy is twice as large there. So 6 kilojoules and 12 kilojoules for those last two. Finally, which way does the energy transfer in the system? From the hotter to the colder. So the one with the higher average kinetic energy to the lower average kinetic energy. What is equilibrium? The point at which energy is done transferring and all the molecules in a system have the same average kinetic energy. And then what is heat? So remember when we touch something cool, we're actually feeling the energy transfer. So heat is the energy transfer that you feel. Some objects might feel hotter or colder than others, even though they're the same temperature, and that all has to do with how fast they are transferring. So you guys can kind of refer to that one. And then the last little thing refers back to those demos that we did on that very first day of this unit. A metal hard drive and a book are left out in the sun for 3 hours on a 100-degree Fahrenheit summer day. That's pretty warm. So true or false, the drive and the book are at the same temperature. The answer here is true because they've both been sitting outside on this 100-degree Fahrenheit day. They both come to equilibrium with the air temperature around them. So they are the exact same temperature, but they don't feel the same because, again, what you're feeling is heat and energy transfer. You're not actually feeling temperature, which is the average kinetic energy of molecules. All right, so when you place your hand on the hard drive or the book, describe which way the energy moves. Because our body temperature is lower than the 100-degree Fahrenheit, our hand is actually cooler than the book and the hard drive. So they should feel warm to us because energy is transferring from the book into our hand. Okay, to the touch, which feels hotter, the hard drive. Okay, and then why does this feel hotter even though they've been in the same conditions for the last 3 hours? Well, because metal is a great conductor of heat. When we touch that, we have more energy transferring into our hand faster than we do with the book. So even though they're the same temperature and they're both going to transfer energy to our hand because our hand is colder, the metal does it at a quicker rate. Okay, same scenario here, but in a cold environment. They're left outside for 8 hours, 0 degrees Celsius. So true or false, the drive and the book are the same temperature. That is true. Okay, they're both at about 0 degrees Celsius. When you place your hand on the hard drive or the book, describe which way the energy is moving. I hope your hand is warmer than 0 degrees Celsius. So if you guys touch either of those, you should have energy moving out of your hand into the book or the hard drive. To the touch, which feels colder, again, the hard drive is going to feel colder. Because it's metal, it has that faster energy transfer. It's going to feel colder, but both of them are cold, and both of our hands are going to be losing energy no matter which one we're touching. But when we touch the metal, because it's a good conductor, we lose heat and energy out of our hand faster. So that's why it feels colder. Okay, that concludes your guys' lesson. Hopefully you guys did well. Maybe go back and touch up your wrap-up to tell me how you guys actually did, and I will talk to you soon.